Welcome everyone to this week's Autonomy Talk. This week is a pleasure to have with us Kevin Smith, directly from California. So thank you for the early talk. Kevin is a lecturer at the University of California, Santa Barbara, in the Center for Control Dynamical Systems and Computation. And something about him. So he received his Bachelor of Science in Physics from Harvey Mudd College in 2017. Then he moved to Santa Barbara, where he obtained first his Master of Science in Electrical and Computer Engineering, and then his PhD recently, working with Professor Francesco Bullo. Also, he was previously affiliated with the Electricity Infrastructure and Buildings Division at the Pacific Northwest National Lab. His research is about dynamics, control, and estimation problems, which typically arise in network systems, and applications include power grids and other infrastructure systems. Today's talk is titled Semicontracting Dynamical Systems, and we are very excited to hear more about the subject. So the stage is yours, Kevin. Go ahead.
Awesome. Well, thank you for the introduction, and thank you all for being here. I'm very excited to be giving a talk with you today and to share some of my research that I've been involved with on the topic of semi-contraction theory. So before I get started, I want to make a couple of acknowledgements of the scientists who I've been collaborating with on this project. So foremost, Julia De Pasquale, who's now actually at ETH, also Elena Belker, and of course my PhD advisor, Francesco Bullo. And I do want to acknowledge as well a couple of papers that most of the content of this talk is going to be based on. So most of the content is going to be based on a manuscript that Julia and I very recently submitted to TAC, but I'm also going to be drawing on a paper that appeared in TAC earlier this year from my colleagues Saber Jafapour and Pedro Cisneros Velarde, which really introduced some of the foundational concepts in semi-contraction theory. So the outline of what I'm going to talk about, I'm going to begin with sort of a high-level introduction to the topic of semi-contracting systems, motivate why we care about them in the first place and what kinds of questions we want to answer in this talk. Then I'm going to get more into the technical details. So I'm going to talk a bit about seminorms, which are sort of the central object of study in semi-contraction theory. Then I'll finally get into some results pertaining to dynamical systems. And then if time allows, I'm going to talk very briefly about some future applications of this line of research. So before we get too much into semi-contraction theory, let's first take a step back and talk about contraction theory to begin with. Okay? So a dynamical system is said to be strongly contracting if any pair of trajectories of that system are exponentially converging to one another. So this is something that I've illustrated below in this little graphic. So we can see that there are two trajectories, one that's black and one that is blue. The blue one starts off within a ball of some radius of the black trajectory. And then you can see that it stays within that ball as the system evolves, even as the radius of that ball is shrinking exponentially in time. Okay, so this exponential convergence of trajectories is really the hallmark of contracting systems. And so that's a fairly strong property that has a number of useful implications. So if you have a contracting system that also has some kind of external forcing, an input term, you get some very nice input to state stability bounds. If your contracting system is time invariant and autonomous, then it turns out you have a unique, globally exponentially stable equilibrium point. Contracting systems also have nice numerical properties as well when you're trying to integrate or simulate them. And so because it has all of these nice properties, contracting systems have found a number of applications, of course, within stability analysis and with control design, but in some other areas as well. So for example, in my PhD research, I've worked on using contraction ideas to solve or to identify solutions of the active power flow equations. I've used it to design physics-informed machine learning models. I've used it fairly recently to study the convergence of an optimal control algorithm. So, contraction is a very powerful idea, and it's also a somewhat versatile idea as well. But of course, not every dynamical system is going to be contracting. And so really the focus of this talk is going to be on two classes of systems that are never contracting because they have a certain property that prevents contraction from occurring. Okay? So those two properties are going to be invariance and conservation. So the invariance property is simply that if you have your vector field F and you translate that vector, you translate your state in some particular direction, then the vector field is going to be invariant under those translations. So this is something that shows up, for example, in dynamics of power systems. If your state variable is a vector of voltage angles, well, typically the dynamics of a power network only depend on differences between adjacent voltage phases. And so if you uniformly rotate all of the phases by some constant amount, then that's not actually going to affect the vector field. Another example would be in swarms of fish or birds or other animals. So if you were to take the swarm and sort of translate it in space, as long as you're not hitting like a rock or a tree or something, the dynamics of that swarm are probably going to look very similar to how they would before the translation, right? There's this idea of invariance. So the other property is conservation. This is something that's very familiar, for example, in a traffic network. So if you have some differential equation model for how traffic is flowing within a road network, that model is going to have to conserve the total mass of cars within the system. So sure, cars can, of course, enter and exit the network at on-ramps or exits of the road, but that corresponds to an external input rather than the actual dynamics itself. So both of these invariance and conservation properties have a differential characterization. So for invariance, what it means is that everywhere in state space, the Jacobian matrix has some particular right kernel. And the conservation property means similarly that there's some particular left kernel. So as I said, systems with invariance or a conservation property are never strongly contracting. And so I've given a visual of this here on the right. So what I've plotted here is a phase portrait of a linear Laplacian flow. So remember, a Laplacian matrix by definition has 0 row sums. So if we take a dynamical system of the form x dot equals minus Lx, it's going to satisfy that invariance property with respect to the span of the vector of ones. And you can see very clearly on this plot, these trajectories, while they are converging to this consensus space, they're not getting closer together exponentially, right? The distance between them is not exponentially decaying. So it's clear that contraction is not going on here. But all hope is not lost. So if you go back to that Laplacian flow system, and instead of looking at the evolution on the full space, if instead you project all of the trajectories onto the subspace that is orthogonal to the vector of ones, well, within this subspace, it sure looks like the system is contracting, doesn't it? So I've plotted a couple sample trajectories here within this orthogonal subspace, and you can see that here they do have this exponential convergence property that you would expect from a contracting system. And so sort of at a high level, that's really what this idea of semi-contraction is about. Semi-contraction is when you have a system that is not contracting overall, but it is contracting on a certain subspace. And so we'd be interested in trying to take the tools from contraction theory to study this contraction on a subspace and see what we can say about the dynamics overall. Right? I think it's a very natural question, but as we're going to see, it's maybe a little bit trickier than it would seem at first glance. So let's warm up a little bit. I'm going to start with some very simple dynamical systems, linear time invariant, one that has an invariance property and one that has a conservation property. Okay. So for both of these systems, let's let A be some row stochastic matrix. And then if we define a discrete time system where A is the Jacobian matrix of that system, right? This is an example of something that's called an averaging system, right? And so I think it's fairly clear that averaging systems satisfy this invariance property, again, within the span of the vector of ones. But on the other hand, if you take the row stochastic matrix and you transpose it, right, now you get another dynamical system, which is called a dynamical flow system. And in this system, instead of invariance being satisfied, now we have a conservation property where the total mass of 1n transpose times the state vector is preserved along system trajectories. Okay, so I just want to point out that a very classic example of a dynamical flow system is, for example, a Markov chain. So these are two classes of systems that have actually been studied for a rather long time, all the way back to Markov in 1906, in fact. And so the study of them involves a quantity, which is called the Markov-Dobrushin ergodic coefficient. Okay. So I've defined this here, this coefficient here. The definition is, it looks a lot like an induced matrix norm, right? So we're maximizing over this product A transpose times Z and taking the L1 norm of that. But the difference between this and a induced matrix norm is that when we're maximizing over Z in the ergodic coefficient, we're restricting Z to be orthogonal to the vector of ones. Okay, so it's a little bit different. Now, ergodic coefficients in general have been used, primarily to study convergence rates of Markov chains. You can define them, using any LP norm that you'd like. The most common one is this L1 ergodic coefficient that I've defined here. And so now, going back to that pair of systems that I introduced, I'm going to show you a pair of very classical results that sort of relate the convergence of these systems to this ergodic coefficient. So starting off, I have a property of averaging systems, right? And so the idea here is that the range of the state of this averaging system is bounded according to this inequality involving the L1 ergodic coefficient. Okay, so what this theorem is saying is that you have this function max minus min. If you compute this function of the state of the averaging system and you evolve it forward in time, well, if tau1 happens to be less than 1, then what's going to happen is this max minus min function is going to go to 0. Okay, and so that implies that the system state is converging to the span of 1n. Okay. So that's one result, one fairly classical result. And then there's another result which pertains to the other class of systems, specifically Markov chains. So in this theorem, this is defined in terms of something called the total variation distance, denoting that dTV here. So the total variation distance is a fairly classical function that measures the difference between two probability distributions, let's say pi and sigma. Okay. And so this is an old result in the convergence of Markov chains, which relates the total variation distance between two trajectories of a Markov chain, again, to the same L1 ergodic coefficient. So again, if tau1 happens to be less than 1, what this theorem implies is that the total variation distance is going to 0, which means that any two trajectories of the Markov chain are converging to the same stationary distribution. So these are two, very old, very prototypical results that talk about sort of this idea. It's not explicitly semi-contraction, but it's the same kind of idea that we're going to be aiming for in the rest of this talk. It also raises a couple of questions, though, right? Because these are two rather different systems, and yet for both of them, this tau1 ergodic coefficient is showing up in both. Okay, so in addition to some of these practical questions about trying to develop semi-contraction theory, some other questions that we're going to look at in this talk is, why is that the case? Why is tau1 relevant to both averaging and dynamical flow systems? And then, why are the corresponding functions, the max minus min and the total variation functions, how are those related? All right. And then we're also going to see how we can extend, using a semi-contraction framework, how we can extend these classical results to more general settings. How can we extend them to continuous time? How can we extend them to time varying and nonlinear systems? And how can we generalize the invariance and conservation properties that they reflect? So maybe I'll take a moment to pause for questions. Has anyone asked anything yet? I think the chat is clear, so I'm going to just keep going then. Okay. So now that I've sort of motivated semi-contraction theory and posed a couple of questions, let's really get into the technical content here and start talking about seminorms, which are the central object of semi-contraction theory. Okay, so a seminorm is really just a norm that's not necessarily positive definite. Okay, so this is the formal definition. The seminorm, we have a function from Rn to a non-negative number. Just like a norm, that function is going to have this absolute homogeneity property. It's also going to satisfy triangle inequality. But the real difference from a seminorm and a norm is that a seminorm has a non-trivial kernel. Okay, so the kernel of a seminorm is the set of vectors where the seminorm is equal to 0. For a norm, this kernel would obviously just be the origin, right? Just that one point. But for a kernel, these can be more general vector spaces. Now, most of the theoretical results that I'm going to share will apply to seminorms that have arbitrary kernels. But for most practical applications, what we're really going to be interested in is seminorms where the kernel is the span of one n, right? This consensus space. And so I'm going to refer to those as consensus seminorms. And one thing to keep in mind is that seminorms are invariant under translations in the kernel. So if you have some vector x, you add some vector u that is in the kernel of the seminorm. The seminorm of x and the seminorm of x plus u are going to be the same number. Okay. One other definition that I want to get out of the way is the concept of an induced matrix seminorm. Okay, so if you have a seminorm in Rn, this induces a seminorm on the space of n by n matrices as well. Okay, and so the induced matrix seminorm is defined for any matrix A. And the definition is very, very similar to an induced matrix norm that you might be familiar with. But the difference is that this vector x that we're maximizing over has to be orthogonal to the kernel. Right, so that looks kind of similar to the ergodic coefficient that I defined before. And in fact, they are related. I'm going to get to that later on in the talk. Okay. And so now a word of warning. When we're working with norms, we're used to there being certain submultiplicativity properties that are satisfied. Right, so if you have a matrix and a vector, and you take the norm of the matrix vector product, that norm is going to be upper bounded by the induced matrix norm times the norm of the vector, right? And that's an inequality that's really at the heart of contraction theory. This isn't always the case with seminorms. Okay, so it is true in some cases. If x happens to be orthogonal to the kernel, this is true. And if the kernel is A invariant, this is also true. But in general, seminorms do not have the same submultiplicativity property that much of the results in contraction theory rely on. Okay, so this is sort of a hint that the study of semi-contraction is going to have some subtleties, and we're going to have to be a little bit careful applying our intuition from contraction theory into the realm of semi-contraction theory. So now let me define some actual concrete classes of seminorms. So Julia and I have proposed two classes of seminorms that we think are very natural. One of them is based on projection. Okay, so I'm calling these projection seminorms. And the idea of a projection seminorm is that you take your vector x, you project it onto the orthogonal complement of the kernel, and then you measure the whatever LP distance you want to choose for that orthogonal component. Okay. The other class of seminorm that we define is a distance seminorm. So distance seminorms don't involve projection. Instead, what we're doing is we find some point on the kernel that is as close as possible to your vector x with respect to some standard LP norm. And then the seminorm, the distance seminorm of x is just going to be the LP norm of the difference between x and this vector u1 kernel. So that's the mathematical definition. Let me show you graphically what this looks like. Okay, so for projection seminorms, again, we have some vector x. We can decompose this vector into a component in blue, which is parallel to the kernel, and a component in red, which is orthogonal to the kernel. And then the projection seminorm of this vector is just going to be some standard LP norm measuring the length of this red component that's in the orthogonal complement of the kernel. So that's projection seminorms. For distance seminorms, again, we're finding some point u that lies on the kernel, and we're trying to minimize this red vector, which is x minus u. Right? To be honest, this picture is actually a little bit misleading because in 2 dimensions, these ideas coincide. Okay, so in 2 dimensions, it happens to be the case that this optimal vector x minus u is in fact going to be orthogonal to the kernel, so the pictures would be the same. But in higher dimensions, that's not always true. So in higher dimensions, the projection and distance seminorms end up being different because this angle of the x minus u vector for the distance seminorm can be at an oblique angle to the kernel. Okay. So projection and distance seminorms are defined for any arbitrary kernel that you feel like. But again, for most practical applications, we are interested in consensus seminorms where the kernel is the span of 1n. And so for this case, we have some explicit formulas for the standard projection and distance seminorms. I'm not going to walk through the math of these in any detail, but something that I do want to point out is that you have probably seen many of these functions before. Okay, so the L1 projection seminorm, it turns out that this gives rise to the total variation distance that I was telling you about a few slides ago. Okay, so the total variation distance between 2 vectors on the simplex is actually equal to the L1 projection seminorm of their difference. The L2 projection seminorm shows up in population games. The L infinity projection seminorm is very similar to a Lyapunov function that I actually used to study transient stability in power networks before I knew anything about semicontraction theory. And the L infinity distance seminorm is proportional to this max minus min function that we saw earlier. Okay. So these functions have been used over and over again in the literature in different sort of ad hoc contexts. I don't think anyone has before sort of realized that these are actually manifestations of the same classes of seminorms. So I think an interesting consequence of starting to look at semicontraction theory is that we start to see that many of these functions are actually unified under this one definition. Okay, so going back to that pair of classical results that I showed you a few slides ago, as I said, the max minus min function is proportional to the L infinity distance seminorm. So for this classical theorem on the convergence of averaging systems, we can actually restate this result in terms of the L infinity distance seminorm. And then for the classical property of Markov chains, because the total variation distance between pi and sigma is proportional to the L1 projection seminorm of their difference, we can restate this Markov chain property in terms of the L1 projection seminorm. So, so far, nothing too groundbreaking. Basically, we've just defined some seminorms, and we've used those definitions to rewrite these 2 theorems. We haven't really proven anything new yet. Okay, but writing them in this form does kind of suggest where we might try to explain why tau1 appears in both of these equations. Okay, so in this first result, we have an A matrix, and in the second result, we have an A transpose matrix. In the first result, we have an L infinity seminorm. In the second result, we have an L1 seminorm. And so in light of those two facts, I bet that some of you in the audience are asking yourself the same question that Julia and I asked ourselves a few months ago, which is, is there some kind of duality result at play here? And the answer is yes, but first let me define what duality means. Okay, so remember that any norm on Rn also induces another norm in Rn that's called the dual norm. And so the way that the dual norm is defined is you take some vector x in Rn. The dual norm of that vector is going to be the maximum value of the inner product with vectors on the unit disk. Right? Technically speaking, dual norms are actually defined in terms of the dual space, which are linear functions from Rn into the reals. But because any function like that you can just represent as the inner product with some vector in Rn, it's very common to just identify the dual space of Rn with itself. Right, so that's what I'm doing here just for the sake of simplicity. So a classical result in linear algebra is that if you have P and Q such that P inverse plus Q inverse is equal to 1, then the corresponding LP and LQ norms are dual. And in fact, the induced matrix norms corresponding to the LP and the LQ norm satisfy an equation, which is that the induced LP norm of the matrix is equal to the induced LQ norm of the matrix transpose. So that's dual norms. Julie and I propose a definition of a dual seminorm, which is rather similar, but again, when we're maximizing over the unit disk, we are restricting the search of these vectors V to be orthogonal to the kernel. Right? And with this definition, we get the property that the dual seminorm is itself a seminorm with the same kernel as the original seminorm. So with this definition of dual seminorm, we get to sort of the first main theorem, which is that projection and distance seminorms are dual. Okay? So if we pick some norms P and Q such that P inverse plus Q inverse is equal to 1, well, the dual seminorm of the LP distance seminorm turns out to be the LQ projection seminorm and vice versa. So there are a couple of useful consequences of this duality result. For any general seminorm and any general matrix, it turns out that the induced LP distance seminorm of this matrix is going to be equal to the induced LQ projection seminorm of its transpose. Specifically, if you're working with consensus seminorms, and specifically for row stochastic matrices, of course, this relationship holds as well, but you also have another equality, which is that these induced norms are equal to the tau q ergodic coefficient. Okay, so in particular, if P is equal to infinity and Q is equal to 1, let's revisit our pair of classical results one last time. Right, so for the property of averaging systems, right, we know due to this duality result at tau 1, we can write this as being equal to the L infinity distance seminorm of A. Okay? And then in the second result, we can write tau 1 is equal to the L1 projection seminorm of A transpose. And so once we've made this substitution, now we see that really what these classical theorems are saying is sort of an elementary result in semicontraction, right? We have these sorts of contraction properties, but with a seminorm instead of a norm. Okay. And this also answers the question of, why does this tau 1 coefficient show up for both of these systems? Well, it's because these two results are essentially two sides of the same coin. Looking at it through the lens of duality, we have a statement about a pair of seminorms that are dual. Okay, so we've answered these first two theoretical questions. Now, for the rest of the talk, I'm going to work on trying to extend these classical results to more general settings, to continuous time and to time-varying nonlinear systems with generalized invariance and conservation properties. I'm going to pause for a moment for questions if anyone wants to ask something, because I know that That was rather technical.
Quick question.
Oh, yeah.
Did you have to deal with the issue that that property that doesn't hold for seminorms, for induced seminorms?
Oh, yeah. So like in the context of this theorem?
Yes.
Yeah, that's a very interesting question. So this theorem is true, right? And what you're alluding to is the fact that in general, if you have a matrix and you have a vector, then as I showed you before, the seminorm is not necessarily submultiplicative, right?
Yes, exactly.
In general, that's the case. There are specific instances where this property does hold. And so one way that you could interpret these two classical results is that these are actually showing you two specific cases where the submultiplicativity property does hold, if that makes sense. Right, so it's not always true, but sometimes it is true. And when it is true, that's when we're gonna be able to find some interesting results in semi-contraction like these. So let's get to the real meat of this talk, which is, of course, semi-contracting dynamical systems. So before I start to talk about semi-contraction, because semi-contraction is built on top of contraction theory, there are a couple of ideas from contraction theory that I need to define first, just to make sure that we are all on the same page. Right, so starting in discrete time, if we have a discrete time system, we say that the system is strongly contracting if the induced norm of the Jacobian matrix is upper bounded by some constant less than 1. Okay. So if that is the case, it turns out that the Lipschitz constant of this function f is upper bounded by rho. And so a consequence of that is you have this these exponentially converging trajectories, which is the sort of characteristic property of contracting systems. So that's discrete time. And of course, there's a similar set of results for continuous time, but in continuous time, instead of working with the induced norm of the Jacobian matrix, we are working with something called the induced logarithmic norm. And I'm showing the equation here purely just to have a formal definition somewhere in the slide deck. I don't expect you to have any intuition for this, because fortunately, when we're working with the standard log norms, there are formulas that explicitly give you the log norm as a function of the entries of the matrix that you can work with instead of using this limit definition. Okay. And there are formulas for the induced norm as well. So I don't want you to memorize these or anything. I just want you to be comforted by the fact that these formulas exist. So continuing on with contraction theory, if we have a continuous time dynamical system, we will say that that system is strongly contracting with some rate c if the log norm of the Jacobian matrix is upper bounded by some negative constant for all time and for all states. And so, of course, if a system is strongly contracting, this implies that the distance with respect to this norm between any pair of trajectories is going to be exponentially decreasing with rate c. There are a parallel set of definitions that extend the ideas of contraction from norms into seminorms. So I'm going to show you these definitions. I want to point out that these were originally proposed by my colleagues Saber Chapapour and Pedro Cisneros Baralde in a TAC paper that appeared earlier this year. Okay, so the extension goes like this. Again, we have an induced logarithmic norm, which is going to be important, but now it's a logarithmic seminorm instead of a norm. The definition is almost exactly the same. The only difference is that we are replacing the norm with a seminorm, as you would expect. Okay. And then we are defining a system to be strongly contracting in continuous time if the induced log seminorm of the Jacobian matrix is upper bounded by a negative constant. So these definitions are almost exactly what you have for contraction theory, but now instead of working with norms, we are working with seminorms as you would expect. And there are also definitions for semi-contraction in discrete time. Just for the purpose of brevity, I'm not going to include those. I'm just going to focus on continuous time because I think it's a slightly more interesting case. Okay. So we have some methods to compute the logarithmic seminorms in general, but it's a little bit more involved than I want to go into right now. So for now, I'm just going to show you some examples of formulas for the log seminorms of negated Laplacian matrices. Again, I don't want you to remember what these are. I just want you to know that they are available. And once again, a word of warning, which is that, for a contracting system, the property that we get, which is very nice, is that the distance between any two trajectories is exponentially decreasing. You might expect that a similar property is true for strongly contracting systems, right, with the seminorm instead of the norm, of course, but that's just not the case, right? With semi-contraction, we have all of these kinds of subtleties that prevent some of this intuition from just being true. And so I have an example here of a counterexample to this bound. I think in the interest of time, I'm not going to go into the details of this, but I just want you to know that it's actually fairly simple to construct counterexamples of this inequality. So let me try to give you a little bit of intuition for why this inequality doesn't hold in general. And to do that, I'm going to take the full system dynamics and I'm going to decompose them into a component that is perpendicular to the kernel in this block on top, and a component that is parallel to the kernel in this block on the bottom. Okay, so if we do this decomposition, of course, we end up with this sort of pair of systems that are interconnected. So strong semi-contraction, all that means is that this vector field in the top block for fixed values of x parallel is strongly contracting, right? But x parallel is not fixed, of course. It's evolving according to its own dynamics within the bottom block. And in fact, the property of strong semi-contraction doesn't tell us anything about how x parallel is evolving. It doesn't tell us anything about how the x parallel component is affecting the dynamics perpendicular to the kernel. Right, and so from strong semi-contraction alone, unless we make some assumptions, right, some additional assumptions beyond that, there's not a lot that we can say about how how the perpendicular component is evolving. But what if we make some assumptions? Okay, are there assumptions that actually lead to this inequality being true? And the answer is yes. And the answer is that there are two special cases where this is true that are sort of generalizing the invariance property that I talked about earlier on, as well as the conservation property. So the first case is when the kernel of the seminorm is F invariant. So a differential characterization of this is that if you have some vector in the kernel and you multiply that vector with the Jacobian matrix at any point, the Jacobian matrix has to map that vector in the kernel back into itself. All right, so that's this idea that the kernel is F invariant. It's fairly easy to see that this generalizes the invariance property that I talked about at the beginning, so long as the kernel of the seminorm and the kernel of the Jacobian matrix coincide. So that's one case. The second case is when the orthogonal complement of the kernel is F invariant. So in this case, again, there is a differential characterization of it. It's a little bit less obvious to see here, but this does generalize the conservation property so long as the left kernel of the Jacobian matrix coincides with the kernel of the seminorm. So I'm going to try to give you a bit of intuition for why this ends up working out. In the first case, if the kernel is F invariant, going back to this, this decomposition for the component of X that's orthogonal to the kernel and the component of X that is parallel to the kernel, if the kernel is F invariant, the interconnection going from the parallel block into the perpendicular block is severed. Okay, so what this means is that the perpendicular dynamics in this special case are actually autonomous. Now, in the second case, it's kind of the opposite. So in the second case, now the parallel dynamics are autonomous. And what that means is that if you have two initial conditions that coincide at least parallel to the kernel, then they're going to then the components of these trajectories parallel to the kernel is going to be the same for all time. Okay, and so what that means is that, sort of hand waving this a bit because I don't want to go into the technical details within this slide. What this means is that you can take the dependence of the perpendicular dynamics on X parallel and sort of absorb that into some time variation of the vector field. In either case, what happens is that the perpendicular components of any two trajectories, so long as this initial condition caveat is satisfied in case 2, these perpendicular components are going to be subject to the same vector fields, and these vector fields are going to be strongly contracting, which leads to the exponential decay of the seminorm distance between the two trajectories. So let me just formally state this now altogether. All right, so if we have a system that is strongly semi-contracting with some rate, then the seminorm distance between any two trajectories is going to be exponentially decreasing with rate c if any of the two conditions hold. The first one, kernel being F invariant, which generalizes the invariance property. The second one being that the orthogonal complement of the kernel is F invariant, and that any difference in initial conditions is orthogonal to the kernel. All right, so interpreting this as an extension of the conservation property, if you have two trajectories of a system that is conserving mass, you wouldn't expect those trajectories to be converging to one another unless the initial mass is the same, right? So that's how I would intuitively explain this extra condition in case 2. So that's the real technical content that I wanted to talk about. I'm going to pause once again for questions if anyone has anything to ask at this point. Okay. So now let me wrap up by talking about some future applications. And let me say that this work is fairly new. So with the future applications, these really are future directions. Applications that I think are promising, but not something that we've really quite fully, fleshed out yet. So keep that in mind. The first application that I think would be promising is in the study of continuous time Markov chains. All right, so remember, a continuous time Markov chain is you have these dynamics pi dot is equal to minus some Laplacian matrix transpose times pi. The state evolves on the simplex. And so from our main theorem, we can see that if the induced log seminorm of these Laplacian matrices have a negative upper bound for all time, then we have this sort of convergence result, which is based on the seminorms. Okay, so this very closely mirrors the kind of applications of ergodic coefficients that you would see in discrete time Markov chains. As far as I know, no one has defined a notion of a continuous time ergodicity coefficient. So I would propose that the log seminorms of these negated transposed Laplacian matrices would be a natural candidate for that, right? Because they describe the convergence rate of the continuous time Markov chain. So another possible future application of this would be to establishing, for example, perturbation bounds in terms of these continuous time ergodic coefficients. So that's one application. Another application is to the study of consensus algorithms. So consensus algorithm, you have a system x dot is equal to minus some Laplacian matrix times x. This Laplacian matrix can be time varying. I think one of the most important results in the study of continuous time averaging dynamics is due to Luc Moreau in 2004. So essentially what his theorem says is that if the digraph, which corresponds to this Laplacian matrix, has a uniformly globally reachable node, and there are some technical details on that I won't go into. If it has a uniformly globally reachable node, then the averaging dynamics are going to converge exponentially to the consensus space, the span of 1n. Now, it turns out that in Moreau's original proof, he's using the L infinity distance seminorm, not explicitly as a seminorm, but just as a Lyapunov function. And so if you take his proof and put it into explicitly a semi-contraction framework, it actually simplifies just a little bit. And it suggests that there may be extensions of this result to averaging dynamics that are nonlinear, or averaging dynamics with perhaps more general properties. Okay. Another application would be to the study of power networks. So if you take a coupled oscillator model for a Drude-controlled inverter network, which is something that I've studied before, turns out that you can use semi-contraction to look at this. So within the power systems context, the idea, one of the most important control ideas is primary frequency control, which is that you want all of the AC frequencies for nodes in the system to converge asymptotically to the same value, right? You want to achieve asymptotic frequency synchronization. Maybe I won't go into the details of this, but a previous project that I had, before I knew anything about semi-contraction theory, used a Lyapunov function that is very similar to the L infinity projection seminorm to prove this kind of convergence result. So I think it would be interesting to go back and see if we can get stronger results, maybe explicit convergence rates using a semi-contraction framework. Oops. And so the last application that I'm going to talk about is to population games. So the elements of a population game, you have a set of pure strategies. You have a population of agents who are trying to select from this set of pure strategies. And that gives rise to something called a population state, which lies on the simplex. So the population state just describes what fraction of the population is adopting each of the n possible pure strategies. And so when in a population game, there's something called a payoff function. Right? So the payoff function is a function of the population state, and it tells you for each pure strategy, given what everyone else is doing in the population state vector, what is the payoff for each of the n pure strategies? So an example of this would be in traffic networks. Let's say that you have 3 routes to get from point A to point B. Well, those 3 routes are your 3 pure strategies. The fraction of people that are taking each of the routes is the population state. And then, sort of the inverse of your travel time on each of these 3 routes is going to be your payoff for taking each one of the pure strategies. Obviously, that payoff is going to depend on the choices that everyone else is making. So there's a very classic notion of a Nash equilibrium. I think I won't explain that formally, but it's the same idea of Nash equilibrium that's everywhere in game theory. Now, in population games, as of late, there's been the study of looking at population games within the context of evolutionary dynamics. And so the realization here is that in real world scenarios, Nash equilibria just aren't that good of a predictor of how people actually behave in the real world, right? So for whatever reason, people don't have full information. People don't behave rationally in a game theoretic sense. Nash equilibria just often don't have very much predictive power. And so to fix that, the idea of evolutionary game theory is that you try to model agents sort of myopically adjusting their strategies as they see their payoff and as they see the current population state. So they're not explicitly going for a Nash equilibrium, but they are trying to improve their own strategies over time in response to payoffs that they've seen. So there are many kinds of evolutionary dynamics that game theorists have come up with. And of course, in general, dynamic equilibria are not necessarily equal to Nash equilibria. So one of the really interesting questions of population game theory is, well, when is that actually the case, right? For what kinds of evolutionary dynamics and what kinds of payoff functions do the evolutionary dynamics actually converge to a Nash equilibrium? And so one powerful tool that has recently emerged for this is the concept of a contractive game. Okay? And it turns out that the condition for a population game to be contractive is actually equivalent to the Jacobian matrix of the payoff function having an L2 projective log seminorm that is non-positive. Right? So this leads to globally asymptotically stable Nash equilibria, not for every evolutionary dynamic, of course, but for a wide range of evolutionary dynamics that game theorists are interested in. So the natural direction here would be, okay, well, the L2 projection seminorm is just one seminorm. If we start looking at other seminorms, perhaps non-Euclidean seminorms, can we certify that a wider range of evolutionary dynamics are going to lead to convergence of Nash equilibria? So let me wrap up with a few conclusions. Leave time for questions. So, really the big idea of this is that semi-contraction theory, it allows you to study properties of systems that are contracting not on the full space, but only on a subspace. Again, you have to be careful when you're studying semi-contraction theory because a lot of your intuition from contraction and from norms doesn't always hold. It only holds in some special cases, like, for example, systems with invariance or conservation properties. Semi-contraction sort of unifies the analysis of averaging systems in Markov chains via the duality of projection and distance seminorms. And I think there are many rich directions for future applications of these ideas. And so I will leave it at that and open the floor to questions.
Thank you, Kevin, for the great talk. Also in Zurich now it's snowing, so I think your talk evoked snow, which is also great. Yes, let's open the stage for questions. You can either write in the chat and I will read it for you, or you can raise your hand and mute yourself and ask directly. So who wants to start?
I will start if you don't mind. So
yes,
Kevin, first of all, thank you very much for the talk. This is very interesting how, I see how the potential of this tool, of this theory that you are developing is, and I understand that still at the early stages, you just made this discovery and now you're trying to figure out how to use it, right? So, one of the things that you mentioned at the beginning, if I remember correctly, is also application machine learning, right? So,
yes.
Is that correct?
So that's an application of contraction theory, not of semi-contraction theory per se.
Okay. So you don't see any particular advantages of the semi-contraction theory in that case? Yeah.
I don't immediately have any ideas in that direction. I wouldn't say that there are no applications. It's the ideas of contraction to machine learning that I'm familiar with is sort of in the realm of models known as implicit neural networks or deep equilibrium models, which sort of instead of defining a layer implicitly as a layer explicitly as like an equation that maps the input to the output. Instead, implicit models sort of define a relationship between the input and output that the layer has to solve. And so contraction is very useful to that. I don't know immediately how I would extend, what directions would be useful for applying semi-contraction to extend that kind of that kind of concept, but I don't want to rule it out entirely.
Okay, yeah, thank you. So if so essentially, but the semi-contraction allows you to extend some of the results of contraction theory to systems that are not contracting, but in a special way, right? So this is
yes.
Yeah. Okay. Okay. So you have to find those. Okay. Thank you, Kevin.
Yeah. Thank you.
All right. Let's see. Any other question?
I have a question.
Go ahead.
So related to the link to Markov chain dynamics. So there are three things that happen with Markov chains. First, you could have irreducible Markov chains or not irreducible Markov chains, which potentially lead to multiple stationary distributions. And on top of that, you could have periodicity, which often involves a somewhat nasty condition on some greatest common divisors and stuff like that.
Right.
So can you relate, do you think there's a way to relate some of the known results in this framework in a simpler manner?
Yeah, so if you have a Markov chain that is strongly semi-contracting, that's going to imply that there is a unique stationary distribution. Right, so that's the one connection that I have in mind. For primitive Markov chains, I'd have to think a little bit more about it. I don't immediately know what the connection is.
Okay, and have you thought about the connection to periodicity?
Oh, sorry, I meant to say periodicity, not primitive.
Okay.
Yeah.
Cool, thanks.
Yeah, thank you.
Thank you, Edzat, for the question. Any other question? Yeah, I actually had one more practical one because you started talking about the applications, and also actually Francesco, your advisor, mentioned some of these applications at CDC in his talk, and I was interested about the power systems application. In particular, I understand this is still at the level of ideas, but what would be so? To what are you comparing yourself then when you're implementing this kind of control based on this theory? So what would be the methods to benchmark? What would be the state of the art or the benchmark towards which you compare?
So I do want to clarify, it's not, at this point, it's not for control design, it's for analysis of control systems that have already been proposed, right? Like proportional Drew control. I think control design would be an interesting idea. It's just not something that I've thought about just yet. In terms of what benchmarks that we're comparing to, so there's been a lot of work on estimates for regions of attraction of coupled oscillator models. Very often you end up with conservative sorts of algebraic conditions, right? Like some norm is upper bounded by some constant, for example, right? That would lead to defining regions that are based on that sort of concept. So that's the benchmark that I would have in mind to see if we actually get improved results with other analytical approaches. Something that is a new direction that I don't want to speak too much about because it's actually not my work. So I don't want to give anything away on this. Would be looking at convergence rates using this framework.
Okay, I see. Thank you very much. Let's see. Are there any other questions? Maybe a final one. Okay, doesn't seem so. So I think, Kevin, you deserved a good start of the day. You still have a long way to go before night. Thank you very much for the great talk, and good luck for the next step in your career as well.
Yeah, thank you all for coming. I've really enjoyed speaking with you today.
Thank you. Take care, and see you all next week for the next talk.